In this talk, I'm going to present our principal account of quantum entanglement. We've published it in these 4 papers. The version I'm going to give is a pedagogical version we're going to be submitting to American Journal of Physics. So we have this trilemma. What to say about the mystery of quantum entanglement to first-year students? You can ignore the mystery. A lot of people do that. You can show the mystery and say, shut up and calculate, because look, the formalism of quantum mechanics maps to the experimental outcomes. No problem. But there is a problem, of course. The formalism doesn't resolve the mystery. The fact that the formalism maps to the experimental outcomes, that is the mystery. You can show the mystery and then share an interpretation like many worlds or de Broglie-Bohm. Most physics professors aren't interested in doing that. So, what do we do at Elizabethtown College? Well, we follow Einstein. What did Einstein do with the mysteries of time dilation and length contraction in the late 1800s? He pivoted to a relativity principle, a principal explanation, pivoted away from a constructive account, which I'll explain in the next slide. So he took the relativity principle, applied it to the speed of light c, reproducing the Minkowski space-time structure, whence time dilation and length contraction. So we're going to take the relativity principle, apply it to the measurement of Planck's constant h, and reproduce the qubit-Hilbert space structure, whence the Bell spin states and quantum entanglement. Over here, Michelson and Morley experiment. They rotated their interferometer and saw no change in the interference pattern. Reference frames in this respect are related by Lorentz boosts. Over here, Stern-Gerlach rotate their magnets and get no change in the deflection pattern. Reference frames over here are related by spatial rotations. Spatial rotations and Lorentz boosts give you your Lorentz transformations. So, all the introductory physics textbooks show how time dilation and length contraction follow from the light postulate. A few even say how the light postulate follows from the relativity principle. Otherwise, there would just be certain frames in which you'd measure Maxwell's predicted value for the speed of light. So Einstein simply extended Galilean relativity from mechanics to include electromagnetism, in fact, all the laws of physics. Now, Einstein points out in this quote that special relativity is a principal theory as opposed to a constructive theory. What is a constructive theory? Well, there you take hypothetically constructed elements, like in the kinetic theory of gases, and you talk about their causal mechanisms and their dynamics. In a principal theory, you explore the mathematical consequences of empirically discovered facts. Thermodynamics is another example there. So why did Einstein produce a principal account of time dilation and length contraction? Well, here's a quote from Einstein, and he said he just despaired of the possibility of coming up with the true laws from constructive efforts. He just couldn't figure it out any more than anyone else could. So he produced a formal principle that would explain the time dilation and length contraction. And today, 116 years later, we still don't have any constructive account. There is no theory of the ether, and physicists have even given up looking. So now let's take that approach and look at the situation over here with the mystery of quantum entanglement. We introduced it at Elizabethtown College using the Mermin device from his famous American Journal of Physics paper, 1981, Bringing Home Atomic World, Quantum Mysteries for Anybody. And in that paper, he has this source, he says, of these particles. They come out, and Alice and Bob have these measurement devices that they can set in settings 1, 2, or 3, and they get red or green outcomes. Okay. And here are the 2 facts concerning the way this Mermin device functions. Fact 1, when Alice and Bob have the same settings, case A, they always get the same outcomes. Half the time red, half the time green. Fact 2, when they have different settings, case B, they get the same outcomes 1/4 of the time and split again. So what's so mysterious about that? Well, Mermin says to account for fact 1, given that the particles don't know how they're going to be measured and they can't communicate in superluminal fashion between the space-like related measurement events, then they must have some sort of instruction sets to guarantee how they will come out in 1, 2, and 3, and they'll match up. If you use instruction sets, however, you find that you have to get agreement in more than 1/3 of the case B trials. That's your Bell inequality. So we see that our fact 1, what we need constructively to account for fact 1, makes sure that we can't accommodate fact 2. That's the mystery. Quantum mechanics violates the Bell inequality. So let's look at the no preferred reference frame applied to the measurement of Planck's constant? Well, Weinberg points out, hey, when we measure an electron's spin with Stern-Gerlach magnets, we're measuring Planck's constant, right? So, if no preferred reference frame applies equally here, as we rotate these Stern-Gerlach magnets, that deflection pattern, being Planck's constant, better be the same. So that's how no preferred reference frame accounts for this empirically discovered fact, exactly like it accounts for the fact that everybody measures the same speed of light, c. Let's look at the classical constructive model that many physicists expected to see when the Stern-Gerlach experiment was conducted. And that is, the atoms come through and they constitute some dipole moment. And suppose you have them coming through and you only got plus and minus coming through it, for this beam at this particular orientation. And if you have this picture, then you'd say, well, my little dipoles are pointed with or against the magnetic field in this particular direction. And as I rotate the magnets then, the amount of that deflection should decrease and decrease and decrease until, when I've rotated 90 degrees, I should get no deflection at all. That would be saying I measured a Planck's constant value of 0. It's the same thing in moving through the ether at the speed of light and standing still next to a light wave, measuring its speed therefore to be 0. So we know this doesn't work. This cannot account for the spin angular momentum that no preferred reference frame says should exist. What are the mathematical consequences now of this empirically discovered fact? Complete this principal explanation here. Well, let's pick off our spin up, right? Z hat spin up state coming through here, and measure with Stern-Gerlach magnets at B hat oriented at beta relative to Z hat. Now, our constructive explanation that doesn't work would tell us that, hey, we know coming through in this particular orientation that our spin is 100% up, and we're going to measure it over here at B hat, so we should get this projection, cosine beta. But you can't measure cosine beta. You can't get a fraction. It always has to be +1 or -1 because of NPRF. So NPRF says we can only accommodate this cosine beta on average. And so, because +1s and -1s can average to a fractional result, right? So that average only projection plus your normalization condition gives you the distribution precisely as we find with our qubit Hilbert space structure. And there's your average. So now let's put a pair of these qubits together, these spin-entangled particles together, in one of the triplet states here, the Mermin device, where you have the same outcomes for the same settings. Alice is going to measure at A hat, Bob at B hat, where A hat makes angle alpha with respect to Z hat, B hat makes angle beta with respect to Z hat, and the angle between A hat and B hat is theta. And we'll let them measure at these particular orientations for A hat and B hat. Those correspond to your 3 settings in the Mermin device. And we're going to look at a particular collection of outcomes for some alpha and some beta and compute our correlation function. And we're going to organize that into, we're going to partition it, right? Organize it according to Alice's equivalence relationship. In other words, her +1 and -1 outcomes. So that's what Bob averages for her +1s, and this is what Bob averages for her -1s. Now, what we'd expect from our classical constructive model, then we would expect that, at the same, when they're aligned, they both would have gotten Alice's +1, but Bob measured at B hat, not aligned with A hat, and therefore he should have gotten his +1, right? Projected down in his new measurement direction, cosine alpha. But of course, can't measure any fractions, +1 or -1. Therefore, in order to conserve our spin angular momentum, we're going to have to do so on average. Okay? So, here's our average only conservation, right, for NPRF. Here are the constraints on our joint probabilities in the joint probability table from below due to NPRF. And put these two things together and you come up with the joint probabilities here, which explain the outcomes, fact 1 and fact 2. Theta equals 0, fact 1, theta equal 120 degrees, gives you exactly fact 2 for the Mermin device. You can complete then your derivation of your correlation function for the triplet states in the symmetry plane by taking those probabilities, the joint probabilities here, and then taking that result and the one you had previously there, and you get your cosine theta. Exactly according to the qubit Hilbert space structure for the Bell spin states, right? A hat dot B hat cosine theta. So here you see the SU2 symmetries, and then you see the planes in which those symmetries hold. Okay, so there is a conservation at work here, but it's something like we don't see at all in classical physics. So for example, let's look at this situation right here. I mean, the average stuff looks beautiful, maps beautifully according to your classical constructive account, but that's the average picture. Look at this case here. When Alice measures +1, Bob needs to be measuring at this 90 degrees, Bob needs to be measuring 0, right? But what's he going to get? He gets that on average. He violates that in a maximal fashion on a trial-by-trial basis, because he either gets +1 or -1. That's as far away as you can possibly get from 0, and they just average to 0. So this kind of conservation, average-only conservation, is very, very odd. Nothing like we see in classical physics. So what we have done is we've avoided our trilemma here that we pointed out at the beginning by pivoting to a principal explanation of quantum entanglement. We followed special relativity exactly. Special relativity takes no preferred reference frame, applies it to the measurement of the speed of light c. In quantum mechanics, we take no preferred reference frame, apply it to the measurement of Planck's constant h. And we can account for, in principal fashion, we can account for time dilation and length contraction here, and we can account for quantum entanglement here. It's been 116 years with no constructive counterpart here. It's been 86 years since the Einstein-Podolsky-Rosen paper introducing quantum entanglement there, and we still have no constructive counterpart. But we do now have the exact same principal explanation for both of these. Thank you.